In 2012, a spacecraft the size of a small car, running on less power than a kitchen light bulb, detected something that rewrote our understanding of where we end and the galaxy begins. Voyager 1, after 35 years of flying, registered a sudden 40-fold spike in plasma density. The solar wind vanished. Galactic cosmic rays flooded its instruments. It had crossed a boundary that scientists had debated for decades but never directly measured. The boundary where interstellar space truly begins. But here is what most people get wrong. That boundary is not a wall. It is not a line. And it is definitely not the edge of the solar system. The real answer is far stranger and far more layered than anyone expected. If you enjoy deep journeys through the most fascinating science humanity has ever uncovered, do me a small favour and hit that like button and subscribe. It genuinely helps this channel grow and lets me keep making content like this for you. Now, settle in, get yourself comfortable, let's begin. Ask anyone where the solar system ends, and you will get a confident answer. Most people point to Pluto. Some will say Neptune. A few might mention the Kuiper Belt, that frozen ring of icy debris beyond the last giant planet. Every answer sounds reasonable. Every answer is incomplete, and the real answer is so much stranger than any of them that it forced scientists to rethink what a solar system even is. The problem starts with a question that sounds like it belongs in a children's textbook. Where does our neighbourhood stop and the space between stars begin? You would think that after 4 centuries of telescopic astronomy, after landing robots on Mars, after photographing black holes, after detecting gravitational waves from colliding neutron stars, humanity would have nailed down something as basic as the size of its own cosmic backyard. We have not. Not because the data is missing, but because the answer depends entirely on what you mean by the word end. This is not a philosophical trick. It is a genuine scientific problem with physical consequences. The solar system does not fade out in one clean step. It fades out in layers, each one defined by a different physical process, each one located at a vastly different distance from the Sun. And the gaps between these layers are not small. They span billions of miles. In some cases, they span trillions. The boundary you choose changes everything about how you understand humanity's position in the galaxy, how you plan future missions, and how you interpret what our most distant spacecraft have actually found. Let us start with the answer most people give, because understanding why it is wrong reveals something important about how the solar system actually works. Pluto orbits the Sun at an average distance of roughly 39 astronomical units. 1 astronomical unit is the distance from the Earth to the Sun, about 93 million miles. So Pluto sits approximately 3.6 billion miles out. For decades, this was the edge, the 9th planet, the last stop. Textbooks drew a neat circle around Pluto's orbit and labelled everything beyond it as outer space, as though the solar system were a walled garden with a clear perimeter fence. When the International Astronomical Union reclassified Pluto as a dwarf planet in 2006, it did not just demote a beloved world. It quietly admitted that the boundary had never been where we thought it was. Neptune, the outermost major planet, orbits at about 30 astronomical units, roughly 2.8 billion miles from the Sun. If you define the solar system by its planets, this is where it ends. Everything beyond Neptune is technically trans-Neptunian space. But this definition ignores an enormous amount of material that is unquestionably bound to the Sun and unquestionably part of our system. The Kuiper Belt alone stretches from approximately 30 to 50 astronomical units and contains hundreds of thousands of icy bodies larger than 20 kilometers across, along with at least 4 recognized dwarf planets. Saying the solar system ends at Neptune is like saying a city ends at its last skyscraper, while ignoring the suburbs, the farmland, and the wilderness that all fall within city limits. Push further out, and you reach the scattered disk, a population of icy objects with highly elliptical orbits that carry them from near the Kuiper belt to distances of several hundred astronomical units. These objects are gravitationally bound to the Sun. They orbit it. They are part of the solar system by any reasonable definition, yet they occupy space so remote that even our most powerful telescopes struggle to detect them unless they happen to swing relatively close on their elongated paths. The dwarf planet Sedna, discovered in 2003, follows an orbit that carries it from about 76 astronomical units at its closest approach to the Sun, out to nearly 937 astronomical units at its farthest. That farthest point lies more than 86 billion miles from the Sun. Sedna takes approximately 11,400 years to complete a single orbit. It is so distant that at its farthest, the Sun would no longer appear as the blazing disk we see from Earth, but as a brilliant pinpoint of light. Still thousands of times brighter than any star, but small enough to be indistinguishable from a star by the naked eye. Yet Sedna is still gravitationally tethered to the Sun, still orbiting, still ours, and Sedna is not even close to the real outer boundary. Beyond the scattered disk, far beyond the reach of any current telescope, lies the Oort cloud. This is a theoretical shell of icy bodies hypothesized by the Dutch astronomer Jan Oort in 1950. It has never been directly observed. No telescope has ever imaged an object confirmed to be in the Oort cloud, but its existence is strongly supported by the orbits of long-period comets, those ghostly visitors that swing through the inner solar system on paths so elongated that they take thousands or even millions of years to complete a single revolution. These comets arrive from every direction, not just along the plane where the planets orbit. This implies a source that is roughly spherical, surrounding the entire solar system like an enormous shell. The numbers involved in describing the Oort cloud are genuinely difficult to process. Its inner edge is poorly constrained, but estimated to begin somewhere between 1,000 and 5,000 astronomical units from the Sun, depending on where the sparse inner population of icy bodies becomes dense enough to be considered a coherent structure. Its outer edge may extend to 100,000 astronomical units, possibly even 200,000. 100,000 astronomical units is approximately 1.6 light-years. For comparison, the nearest star to the Sun, Proxima Centauri, lies about 4.2 light-years away. At its most conservative estimated extent, the Oort cloud would reach roughly a third of the way to the nearest neighbouring star. At the upper estimates, it could stretch 3/4 of the way there. It is so vast that light from the Sun takes more than a year to reach its outer boundary. Voyager 1, the farthest human-made object from Earth, is currently about 167 astronomical units away. At its current speed of roughly 3.6 astronomical units per year, Voyager 1 will not reach the inner edge of the Oort cloud for approximately 300 years. It will not exit the outer edge for roughly 30,000 years. If you define the solar system as everything gravitationally bound to the Sun, the Oort cloud is the answer. Its outer edge marks the point where the Sun's gravitational pull weakens to the point that the tidal forces of the Milky Way galaxy and the gravitational influence of passing stars begin to dominate. This boundary is defined by the Sun's heliosphere, the region within which objects can maintain stable orbits around our star rather than being pulled away by external gravitational forces. Beyond this limit, objects belong to the galaxy, not to the Sun. The Oort cloud, therefore, represents the cosmographic boundary of the solar system. It is the last region where the Sun's gravity claims sovereignty. But here is where everything gets complicated. The Oort cloud sits entirely within interstellar space. Pause and take that in, because it is one of the most counterintuitive facts in all of astronomy. The Oort cloud is part of the solar system. It is also in interstellar space. Both statements are true simultaneously. This is possible because interstellar space is not defined by gravity. It is defined by something else entirely. Something that creates a boundary much closer to the Sun and much more physically dramatic than the slow gravitational fade-out at the Oort cloud's edge. That something is the solar wind. The sun does not just emit light, it emits a constant torrent of charged particles, mostly protons and electrons, racing away from the sun in every direction at enormous speeds. This flow of material is called the solar wind, and it drags the sun's magnetic field along with it, pulling that field into a vast, invisible structure that reaches far beyond the orbit of every planet. The solar wind is relentless. Born in the superheated corona where temperatures reach millions of degrees, it races outward faster than any sound wave could travel through the surrounding plasma, and it blows with enough cumulative force to shape the space around our star into a vast bubble. This bubble is called the heliosphere. It is inflated by the solar wind, maintained by the sun's continuous outpouring of energy and particles, and it extends far beyond the orbit of every planet, far beyond the Kuiper belt, far beyond anything you can see with your eyes or a backyard telescope. The heliosphere is the sun's domain in a way that has nothing to do with gravity. It is the region where the sun's plasma and magnetic field dominate the local environment. Inside the heliosphere, the space around you is filled with solar material. The magnetic field you would measure is the sun's magnetic field, carried outward by the wind. The charged particles zipping past are solar particles, born in the corona, accelerated outward, filling the bubble with a thin but measurable soup of solar plasma. Outside the heliosphere, everything changes. The plasma is no longer solar. It belongs to the interstellar medium, the material that fills the vast spaces between the stars. This material is fundamentally different from the solar wind. It is colder, it is denser. It is composed largely of hydrogen and helium atoms, many of which were seeded by ancient supernovae that exploded millions of years before our sun even formed. The magnetic field outside the heliosphere is not the sun's field. It is the galactic magnetic field, shaped by processes that span the entire Milky Way. The charged particles outside the bubble include galactic cosmic rays, high-energy particles accelerated by distant astrophysical events like supernova remnants and active galactic nuclei. Inside the heliosphere, the sun's magnetic field deflects most of these cosmic rays, shielding the planets from the worst of the galaxy's radiation environment. Outside the bubble, that shield is gone. The boundary where the solar wind's outward pressure finally balances against the inward pressure of the interstellar medium is called the heliopause. It is the outermost edge of the heliosphere, and it is what scientists most commonly mean when they talk about the boundary where interstellar space begins. The heliopause is not at 100,000 astronomical units. It is not even close. Voyager 1 crossed it on August 25, 2012, at a distance of approximately 122 astronomical units from the Sun. Voyager 2 crossed it on November 5, 2018, at approximately 119 astronomical units. These distances are enormous by human standards, roughly 11 to 11.5 billion miles, but they are tiny compared to the Oort cloud. The heliopause is more than 800 times closer to the Sun than the Oort cloud's outer edge. It is a boundary defined not by gravity slowly loosening its grip over thousands of astronomical units, but by a dramatic environmental shift that happens over a remarkably short distance. When Voyager 1 crossed the heliopause, the environment around the spacecraft changed fundamentally. Solar wind particles essentially vanished from its instruments. Galactic cosmic rays, which had been gradually increasing for years, surged to levels consistent with the full intensity of the interstellar medium. The plasma surrounding the spacecraft was no longer solar in origin. It was interstellar. The spacecraft had transitioned from an environment shaped by the Sun to an environment shaped by the galaxy. This was not a gradual fade-out over millions of miles. The actual crossing happened over a distance that was startlingly thin, astronomically speaking. Voyager 2's more complete instrument suite later confirmed that the transition included a boundary region roughly 1.5 astronomical units wide, where conditions shifted rapidly, but the final heliopause crossing itself occurred in less than a single day. This is the boundary that most scientists refer to when they say a spacecraft has entered interstellar space. NASA uses this definition. The Voyager science team uses this definition. When headlines announced that Voyager 1 had left the solar system, what they meant, or should have meant, was that Voyager 1 had crossed the heliopause and entered the interstellar medium, but it had not left the solar system in the gravitational sense. It is still well within the Sun's gravitational influence. It will remain so for tens of thousands of years. This distinction matters enormously, and getting it wrong leads to widespread confusion. When Voyager 1 crossed the heliopause in 2012, news outlets around the world declared that it had left the solar system. Technically, by the plasma definition, it had entered interstellar space, but by the gravitational definition, it had barely begun its journey through the solar system's outermost reaches. These are not competing opinions. They are different physical definitions measuring different things. The heliopause marks the edge of the Sun's particle and magnetic influence. The Oort cloud marks the edge of the Sun's gravitational influence. Both are real. Both are scientifically meaningful. And they are separated by a factor of roughly 1,000 in distance. Imagine standing in a house during a thunderstorm. The walls of the house block the wind and rain. Inside, you are dry. Outside, you are soaked. The walls represent the heliopause, the boundary between the Sun's sheltered environment and the harsher interstellar medium. But the property line of your land extends much further than the walls of the house. Your yard, your driveway, your fence at the far edge of the lot, those represent the Oort cloud. You can step outside the house and be exposed to the storm while still standing on your own property. That is what Voyager has done. It stepped outside the Sun's protective walls and into the galactic weather, but it is still on the Sun's land. This layered structure means that there is no single answer to where the solar system ends. There are at least 3 meaningful boundaries, each corresponding to a different physical process. The first is the orbit of the outermost major planet, Neptune, at about 30 astronomical units. This is the boundary of the planetary system, the region where large worlds orbit in relatively organized fashion. The second is the heliopause, at roughly 120 astronomical units, where the Sun's plasma influence gives way to the interstellar medium. The third is the outer edge of the Oort cloud, at perhaps 100,000 astronomical units, where the Sun's gravitational dominance finally yields to the galaxy. Each boundary tells a different story about the Sun's relationship with its surroundings. The planetary boundary tells you where the Sun built worlds massive enough to clear their orbits and maintain stable systems of moons and rings. The heliopause tells you where the Sun's continuous outpouring of energy and matter reaches its limit, pushed back by the pressure of the galaxy pressing inward. The Oort cloud boundary tells you where the Sun's gravity, the weakest but longest reaching of these influences, finally loosens its hold and allows the galaxy to claim what lies beyond. Most people never think about the space beyond the planets because it seems empty. No glowing worlds, no dramatic rings, no colourful nebulae, just blackness. But that space is not empty. It is filled with the solar wind, threading outward at hundreds of kilometres per second. It is structured by the Sun's magnetic field, which twists and folds as the Sun rotates, creating a complex 3-dimensional architecture called the heliospheric current sheet, a vast undulating membrane of magnetic polarity that spirals outward like a ballerina's skirt. It is populated by energetic particles, both solar and galactic, whose intensities shift and change as you move outward through the heliosphere's layers. And it is bounded, ultimately, by a transition so sharp and so physically dramatic that when our most distant spacecraft crossed it, there was no ambiguity. The environment changed, the particles changed, the plasma changed, the magnetic field changed. Everything about the space surrounding the spacecraft became fundamentally different in a matter of hours. That transition is what scientists have spent decades trying to understand. Not just where it is, but what it is. What physically happens at the boundary. Why it exists where it does. How it moves and changes over time. And what it means for anything that crosses it. Before the Voyagers reached the heliopause, scientists could only theorize about its location and properties. Early estimates in the 1960s and 70s placed the termination shock, the inner boundary of the heliosphere's outermost region, as close as the orbit of Jupiter, a mere 5 astronomical units from the Sun. As spacecraft travelled farther and the termination shock failed to appear, estimates kept climbing. 10 astronomical units, 20, 50. The boundary kept receding ahead of the probes like a mirage in a desert. It took Voyager 1 more than 27 years of continuous flight just to reach the termination shock, and another 8 years beyond that to finally cross the heliopause at 122 astronomical units. The journey took 35 years from launch, 35 years of continuous flight at speeds exceeding 38,000 miles per hour, and when the crossing finally came, it raised as many questions as it answered. The heliopause was not where some models predicted. The magnetic field on the interstellar side was not oriented the way most scientists expected. The temperature in the boundary region was far higher than anticipated. And the region just beyond the heliopause turned out to be not the calm, undisturbed interstellar medium that textbooks described, but a perturbed, dynamic transitional zone, still bearing the imprint of the Sun's influence. The boundary was real, it was measurable, it was crossed, but it was not simple. Understanding what the Voyagers found requires understanding the heliosphere itself, not as a static bubble floating in space, but as a living, breathing, constantly shifting structure shaped by the Sun's activity, sculpted by the interstellar medium and layered with distinct physical regions that each behave differently. The heliosphere has an anatomy. It has an interior and an exterior. It has shock fronts and turbulent zones and compressed regions where the physics changes dramatically over short distances. To understand the boundary where interstellar space begins, you first have to understand what that boundary is made of. The Sun creates this structure every second of every day. It has been doing so for 4.5 billion years and shows no sign of stopping for billions more. For as long as the Sun burns, it will blow its bubble. And for as long as the bubble exists, there will be a boundary where the Sun's influence ends and the galaxy's begins. That boundary is what 2 small spacecraft, each carrying less computing power than a modern digital watch, each running on the radioactive decay of a few kilograms of plutonium, managed to find after crossing billions of miles of empty space. They did not find a wall. They did not find a gate. They found a transition, a place where the rules change, where the environment shifts from solar to galactic, where the Sun's protective hand finally lets go. What they measured when they crossed it reveals one of the most intricate and surprising boundaries in all of nature, and it starts with a shock wave that no one expected to be so far from home. The Sun is not quiet. It looks peaceful from Earth, a steady golden disk hanging in the sky, unchanging from one day to the next. But that appearance is a lie told by distance. The Sun is a thermonuclear engine converting 600 million tons of hydrogen into helium every second. Its surface churns at temperatures of roughly 5,500 degrees Celsius, and its outer atmosphere, the corona, defies intuition entirely. The corona is hundreds of times hotter than the surface below it, reaching temperatures of 1 to 3 million degrees. Scientists still do not fully understand why the corona is so hot, but they understand what that extreme heat does. It launches material into space. The corona is so hot that the Sun's gravity cannot hold on to all of it. Particles in the corona move fast enough to escape, streaming outward in every direction as a continuous flow of charged plasma. This is the solar wind. It is not a gentle breeze. It is a supersonic torrent of protons, electrons, and heavier ions, pouring out of the Sun at speeds ranging from 300 to 800 kilometers per second. At its fastest, the solar wind crosses the distance from the Sun to the Earth in roughly 2 days. It does not stop at Earth. It does not stop at Jupiter. It does not stop at Neptune. It keeps going, racing outward through the solar system, carrying with it the Sun's magnetic field, stretching and twisting that field into an enormous spiral pattern that fills the space between the planets and extends billions of miles beyond the last one. The solar wind is thin by any terrestrial standard. Near Earth's orbit, it contains only about 5 to 10 particles per cubic centimetre. For comparison, the air you are breathing right now contains roughly 25 quintillion molecules per cubic centimetre. The solar wind is a vacuum by earthly definitions. But it is a vacuum with velocity, with temperature, with magnetic structure, and with enough cumulative pressure across the enormous area of its outward flow to inflate a bubble billions of miles wide. That bubble is the heliosphere. Think of the heliosphere as a boat moving through water. The sun is the engine, the solar wind is the wake, and the interstellar medium, the gas and dust and plasma that fills the space between the stars, is the ocean. The boat pushes through the water, creating a disturbed region around itself. Ahead of the boat, the water piles up and deflects around the hull. Behind the boat, a turbulent wake stretches out. The shape of the disturbance depends on how fast the boat moves and how dense the water is. The heliosphere works the same way. The sun moves through the local interstellar medium at roughly 26 kilometers per second, and the solar wind blows outward against the incoming interstellar material. The result is a bubble that is not spherical. It is elongated, compressed on the side facing the direction of the sun's motion through the galaxy, and stretched into a long tail on the opposite side. Some models suggest the tail extends for thousands of astronomical units. Others propose a more rounded shape. The exact geometry remains one of the open questions in heliophysics, debated actively by researchers using data from Voyager, the Interstellar Boundary Explorer, and computer simulations. But there is something critically important about the heliosphere that complicates the picture before we even reach its outer layers. The bubble is not sealed, it leaks, and it leaks by design. The interstellar medium surrounding the heliosphere is not pure plasma. It is roughly 2/3 neutral atoms and 1/3 ionized plasma. The heliopause, as a magnetic and plasma pressure boundary, is effective at keeping the interstellar plasma out. Magnetized plasmas resist mixing. The solar wind plasma and the interstellar plasma stay on their respective sides of the heliopause, separated by their magnetic fields. But neutral atoms carry no electric charge. They are invisible to magnetic fields. They pass through the heliopause as though it does not exist, drifting inward through the heliosphere on trajectories determined only by their thermal motion and the sun's gravitational pull. This constant infiltration of interstellar neutral atoms has profound consequences for the heliosphere's structure. As these atoms drift inward, they eventually encounter the solar wind or the sun's ultraviolet radiation. When a neutral interstellar hydrogen atom collides with a solar wind proton, the two can exchange an electric charge. The formerly neutral interstellar atom becomes an ion, suddenly subject to the sun's magnetic field, which grabs it and accelerates it outward with the solar wind. Scientists call these newly created ions pickup ions, because they are picked up by the magnetic field and swept along with the solar wind flow. The process simultaneously creates a new neutral atom from the former solar wind proton, which is no longer bound by the magnetic field and can fly off in any direction, sometimes back toward the outer heliosphere or beyond. This charge exchange process does not just create individual particles, it reshapes the heliosphere itself. Pickup ions are far more energetic than the ambient solar wind because they are born with velocities determined by the relative motion between the interstellar inflow and the solar wind outflow. As they accumulate, they add pressure and heat to the solar wind, gradually slowing it and modifying its properties at large distances from the sun. By the time the solar wind reaches the outer heliosphere beyond roughly 30 astronomical units, pickup ions contribute a significant fraction of the total plasma pressure. They are not a minor contaminant. They are a major structural component of the outer heliosphere, fundamentally altering the solar wind's behavior long before it reaches the termination shock. The infiltration of interstellar neutrals also creates a feature at the heliosphere's leading edge that was predicted theoretically and later confirmed by observation. As the heliosphere plows through the interstellar medium, neutral hydrogen atoms approaching the boundary are subjected to charge exchange with the compressed, decelerated solar wind plasma in the outer heliosheath. Many of these atoms are slowed, deflected, or converted into new populations of slower-moving neutrals that pile up just outside and ahead of the heliosphere's nose. This accumulation creates a region of enhanced neutral hydrogen density known as the hydrogen wall. It is not a solid structure. It is a statistical pileup, a zone where neutral hydrogen is denser than in either the undisturbed interstellar medium farther away or the inner heliosphere closer to the Sun. The hydrogen wall was first detected indirectly in the 1990s through its effect on ultraviolet absorption measurements of nearby stars. In 2018, NASA's New Horizons spacecraft, then travelling through the outer heliosphere beyond Pluto's orbit, confirmed the detection by measuring ultraviolet light scattered by interstellar hydrogen. The glow of the hydrogen wall was distinguishable from the background, providing further confirmation that the heliosphere's boundary is not a clean surface, but a complex interaction zone where solar and interstellar material mix, exchange charges, and create new structures that belong fully to neither environment. The heliosphere, in other words, is permeable. Interstellar material flows through it constantly. Solar material leaks out. The boundary is defined by plasma and magnetic fields, but it is porous to neutral particles, and those neutral particles reshape the bubble from the inside out. This is one reason why the boundary is so much more complex than a simple wall or membrane. It exists in full force for charged particles and barely exists at all for neutral atoms. The same location in space can be simultaneously inside the heliosphere for a proton and outside it for a hydrogen atom. The boundary is real, but it depends on what you are. What is not debated is that the heliosphere has internal structure. It is not a uniform bubble of solar wind with a single boundary at the edge. It is layered, and each layer represents a different physical regime where the solar wind behaves differently. Understanding these layers is essential to understanding what Voyager actually crossed, because the spacecraft did not simply fly from inside the bubble to outside the bubble in a single step. It passed through multiple distinct regions, each one marking a different stage in the solar wind's confrontation with the interstellar medium. The first layer is the most familiar. It is the region of supersonic solar wind that fills most of the heliosphere, from the Sun outward to roughly 80 to 100 astronomical units. In this region, the solar wind flows freely. It is still supersonic, meaning it moves faster than the speed at which pressure waves can propagate through the plasma. This is analogous to a jet aircraft flying faster than the speed of sound. Inside this region, the solar wind cannot know what lies ahead. Information about the interstellar medium pressing inward cannot travel upstream against the supersonic flow. The wind just blows, unaware that it is about to hit a wall. But it does hit a wall, or rather, it hits a shock. The termination shock is the first major boundary within the heliosphere. It is the point where the solar wind abruptly decelerates from supersonic to subsonic speed. This happens because the interstellar medium exerts inward pressure on the heliosphere, and the solar wind eventually cannot maintain its supersonic velocity against that resistance. The deceleration is not gradual. It is a shock front, a sudden discontinuity where conditions change dramatically over a very short distance. On the upstream side of the termination shock, the solar wind is fast, relatively cool, and flowing freely outward. On the downstream side, the wind has been compressed, heated, and slowed to subsonic speeds. The kinetic energy of the wind's outward motion is converted into thermal energy. The plasma heats up, the magnetic field strengthens, the density increases. Voyager 1 crossed the termination shock on December 16, 2004, at a distance of approximately 94 astronomical units from the Sun. 3 years later, Voyager 2 crossed it at approximately 84 astronomical units, 10 astronomical units closer to the Sun. This difference was significant. It told scientists that the termination shock is not a fixed boundary at a constant distance. It moves. It breathes. It responds to changes in the solar wind's pressure and to variations in the interstellar medium's resistance. When the Sun is more active, pumping out stronger solar wind, the termination shock gets pushed farther out. When the Sun is quieter, the shock contracts inward. The 11-year solar activity cycle modulates the position of this boundary by roughly 10 to 20 astronomical units, a range comparable to the distance from the Sun to Saturn at the lower end, and from the Sun to Uranus at the upper end. The fact that the two Voyagers crossed the termination shock at different distances was not surprising in principle. Scientists expected the boundary to move. What was surprising was the detailed nature of what they found there. Voyager 1's crossing happened during a data gap, a period when the spacecraft was not being tracked by the Deep Space Network. Scientists had to reconstruct the crossing from data recorded before and after the event. Voyager 2, however, crossed the shock while being monitored in near real time, and its more complete instrument suite captured the transition in detail. What both spacecraft found challenged existing models. The termination shock was supposed to be a powerful accelerator of particles, the place where anomalous cosmic rays, a population of energetic particles observed throughout the heliosphere, received their enormous energies. Instead, the intensity of anomalous cosmic rays at the shock was lower than expected. The source of these particles was apparently not located at the termination shock in the direction Voyager was travelling. It was somewhere else along the shock surface, probably in a region the spacecraft never visited. This discovery forced scientists to rethink their models of particle acceleration at the heliosphere's edge. The termination shock was real, but it was not doing what many researchers had predicted. Beyond the termination shock lies the heliosheath. This is the broad, turbulent, compressed region between the termination shock and the heliopause. If the termination shock is where the solar wind gets punched in the face, the heliosheath is where it staggers around trying to regain its balance. The plasma in the heliosheath is subsonic, meaning pressure waves can now propagate through it. It is hot, compressed, and turbulent. The solar wind, no longer flowing freely outward, gets deflected sideways, turning away from the nose of the heliosphere and flowing down toward the tail. The magnetic field in the heliosheath is amplified and disordered compared to the clean spiral pattern in the supersonic wind region. Large-scale structures, including merged interaction regions created by variations in the solar wind's speed and density, survive out to these distances and create complex patterns of compression and rarefaction in the heliosheath plasma. The heliosheath is not a thin shell. Voyager 1 spent approximately 8 years traversing it, from 2004 to 2012, covering roughly 28 astronomical units. Voyager 2 spent approximately 11 years in the heliosheath, from 2007 to 2018, covering roughly 35 astronomical units. During those years, both spacecraft measured conditions that were far more dynamic and variable than simple models had predicted. The heliosheath was not a calm transition zone. It was a roiling, chaotic region where the solar wind fought its last battle against the interstellar medium. One of the strangest discoveries in the heliosheath came from Voyager 1 in late 2011. NASA announced that the spacecraft had entered a region they called cosmic purgatory, a stagnation zone where the outward velocity of the solar wind had dropped essentially to zero. The solar wind was no longer moving outward. It was piling up, compressed against the approaching heliopause like traffic backing up behind a bottleneck. At the same time, the intensity of energetic particles from inside the heliosphere dropped by nearly half, while high-energy electrons from outside the heliosphere increased 100-fold. The Sun's magnetic field doubled in strength, suggesting that interstellar space was pressing inward, squeezing the heliosheath like a fist closing around a balloon. This stagnation region extended from approximately 113 astronomical units outward, and it represented the final phase of the solar wind's existence before the heliopause. The heliopause itself is the outermost boundary of the heliosphere. It is the surface where the outward pressure of the solar wind plasma finally balances against the inward pressure of the interstellar medium. On one side, the plasma is solar in origin, hot and sparse, carried outward from the corona. On the other side, the plasma is interstellar, colder and denser, flowing around the heliosphere like a river flowing around a stone. The heliopause is where these two fundamentally different plasma populations meet and are forced to stay apart. Because both plasmas are magnetized, they cannot mix freely. Magnetic fields act as barriers, preventing the solar plasma from simply blending into the interstellar plasma. Instead, a boundary forms, thin by astronomical standards, but physically real and measurable. When the two Voyager spacecraft crossed the heliopause years apart and at different locations along its surface, they encountered it at remarkably similar distances from the Sun, both near 120 astronomical units. The fact that both crossings occurred at roughly similar distances from the Sun, despite happening 6 years apart and at different phases of the solar cycle, surprised scientists. They had expected the heliopause to shift significantly with the Sun's activity, expanding during solar maximum when the wind is stronger and contracting during solar minimum when the wind weakens. The relatively consistent distance suggested that the interstellar medium's pressure plays a larger role in setting the heliopause position than some models had assumed. The heliosphere is not inflated solely by the Sun. It is sculpted equally by what pushes back from outside. The measurements at the heliopause revealed several surprises that are still being analysed years later. The first surprise was the magnetic field. When Voyager 1 crossed the boundary, the magnetic field direction barely changed. The magnitude shifted, but the orientation remained parallel to what had been measured inside the heliosphere. This created significant confusion and delayed the official confirmation that Voyager 1 had entered interstellar space, as scientists had expected a clear change in field direction to mark the crossing. The full story of that debate unfolded through the measurements themselves, but the structural implication was clear. The heliopause does not cleanly separate two differently oriented magnetic environments. The fields on either side are aligned, and understanding why remains an open problem in heliophysics. The second surprise was the temperature. The plasma in the very local interstellar medium, the region just outside the heliopause, was far hotter than expected. Voyager 2's direct plasma measurements indicated temperatures of roughly 30,000 Kelvin, approximately 4 times higher than the 7,500 Kelvin predicted for the undisturbed local interstellar medium. Separate measurements of plasma populations in the heliosheath boundary region recorded even higher energies, with some analyses suggesting equivalent temperatures approaching 50,000 Kelvin in the compressed transition zone near the heliopause. Astronomers had previously estimated the temperature of the undisturbed local interstellar medium at roughly 7,500 Kelvin, based on observations of nearby stars and the spectral properties of interstellar gas. The much higher temperatures measured by Voyager suggest that the region just outside the heliopause is not undisturbed at all. It is heated, probably by the interaction between the heliosphere and the interstellar medium. The heliosphere, ploughing through interstellar space, creates compression and heating in the material immediately surrounding it, just as a fast-moving object heats the air in front of it. The boundary region is not a calm interface. It is energetically active. It is critical to understand what temperature means in this context, because it is easy to picture a wall of searing heat, and that picture is wrong. Temperature in plasma physics measures the average kinetic energy of particles, essentially how fast they are moving. A plasma at 49,000 Kelvin contains particles moving at high speeds. But the density is so astonishingly low, just a handful of particles per cubic centimetre, that there is almost no thermal energy in any given volume by human standards. You could fly through this plasma and never feel warmth. The particles are fast, but they are so few and so far apart that collisions are extraordinarily rare. The heat is real, in a physics sense. It is meaningless in a human sense. The third surprise was the density transition. The interstellar medium, even in the Sun's local neighbourhood, is substantially denser than the solar wind at the outermost reaches of the heliosphere. The solar wind has been spreading outward across billions of miles, thinning as it goes, so that by the time it reaches the heliopause, it is extraordinarily sparse even by space standards. The interstellar medium beyond the boundary, while vanishingly thin by any earthly measure, is dramatically denser by comparison. This density contrast is sharp enough to be directly measurable and represents one of the clearest physical signatures that a spacecraft has crossed from one environment to the other. It is what makes the heliopause a real, detectable boundary rather than a theoretical concept. Voyager 2 added a crucial capability that its twin lacked. Its plasma science instrument, the detector designed to directly capture and analyze bulk plasma particles, was still functioning when it reached the heliopause in 2018. This meant Voyager 2 could do something Voyager 1 never could at the boundary. It could directly measure the speed, temperature, and density of the plasma on both sides of the heliopause as it crossed. It provided the first direct plasma measurements at the transition from solar wind to interstellar medium. What Voyager 2 found was a crossing that was even more structured than Voyager 1 had suggested. Approximately 1.5 astronomical units before the heliopause, Voyager 2 entered a boundary region where conditions began changing rapidly. The plasma slowed down, its temperature increased. Its density roughly doubled compared to the typical heliosheath values. This boundary region represented the final compression zone, where the solar wind piled up against the heliopause before being forced sideways. Then, approximately 0.06 astronomical units before the heliopause itself, an even thinner boundary layer appeared where the radial outward speed of the plasma dropped sharply, and the density and magnetic field spiked. The final heliopause crossing occurred in less than a single day. The transition from solar plasma to interstellar plasma was abrupt. But crossing the heliopause did not mean entering the calm, undisturbed interstellar medium that textbooks described. Both Voyager spacecraft found that the region just beyond the heliopause is what scientists now call the very local interstellar medium, and it is not the pristine galactic environment that exists far from any star. It is a perturbed dynamic zone where the interstellar medium still bears the imprint of its interaction with the heliosphere. Pressure waves from solar activity propagate outward through the heliopause and into the nearby interstellar medium, creating disturbances that travel at the local sound speed. Voyager 1 has detected multiple such events, where increases in plasma density and magnetic field strength in the very local interstellar medium correlate with solar eruptions that occurred more than a year earlier. The sun's influence does not stop perfectly at the heliopause. It leaks. Scientists confirmed that the interstellar plasma density continued increasing as Voyager 1 moved farther from the heliopause. This gradual increase suggests that interstellar material may be piling up near the boundary, compressed by the heliosphere pushing through it. One researcher compared it to snow accumulating in front of a plough. The density may eventually reach a peak and then decrease back to the background level of the undisturbed interstellar medium at some greater distance. But neither Voyager has travelled far enough to reach that undisturbed state yet. As of early 2026, Voyager 1 has travelled roughly 45 astronomical units beyond the heliopause, and Voyager 2 approximately 22 astronomical units past its own crossing point. Both are still measuring conditions in the perturbed zone, sending back data that reveals an interstellar environment more complex and more connected to the Sun than anyone anticipated. There is another feature of the heliosphere's interaction with the interstellar medium that scientists expected to find, but apparently does not exist, at least not in the form originally predicted. For decades, models predicted that the Sun's motion through the interstellar medium would create a bow shock, a standing shock wave in the interstellar plasma ahead of the heliosphere, similar to the sonic boom created by a supersonic aircraft. The idea made intuitive sense. The Sun moves through the interstellar medium at roughly 26 kilometers per second. If this speed exceeded the local sound speed in the interstellar plasma, a shock would form upstream. But data from the Interstellar Boundary Explorer, or IBEX, suggested in 2012 that the Sun's speed, relative to the interstellar medium, is slightly too low to generate a true bow shock. Instead, there may be a gentler bow wave, a compression without a sharp discontinuity. The interstellar medium ahead of the heliosphere is likely piled up and heated, but not shocked. This distinction matters because it affects the shape of the heliosphere and the conditions that interstellar material encounters before being deflected around the bubble. The heliosphere also interacts with the interstellar medium in ways that produce completely unexpected features. The Interstellar Boundary Explorer, IBEX, launched in 2008, discovered a narrow ribbon of enhanced emissions at the heliosphere's edge that no model had predicted. This ribbon and its implications for heliospheric structure are part of a larger story of measurement breakthroughs that revealed the boundary's true complexity. But its very existence demonstrated something important about the heliosphere's anatomy. The bubble is not just passively sitting in the interstellar medium, it is actively shaped by the external magnetic field and pressure environment in ways that produce structures visible only through specialized detection techniques. Resolving the mystery of the ribbon, refining the shape of the heliosphere, and understanding the perturbed transitional zone beyond the heliopause are among the primary goals of NASA's newest heliophysics mission. The Interstellar Mapping and Acceleration Probe, or IMAP, now operational and actively collecting data. IMAP carries a suite of 10 scientific instruments, representing a generational leap in capability over its predecessor, IBEX. From its position sunward of Earth, it intercepts energetic neutral atoms streaming inward from the heliosphere's boundary, atomic messengers that carry information about plasma conditions billions of miles away. What IMAP sees with those instruments, and how dramatically it improves upon IBEX's pioneering but limited maps, is already beginning to reshape our understanding of the boundary. But its presence in the observational landscape marks a turning point. For the first time, scientists have a dedicated observatory capable of watching the heliosphere's boundary change in something approaching real time, rather than piecing together snapshots separated by months or years. The heliosphere is not a permanent fixture. It exists only because the sun is actively producing a solar wind. If the sun were to suddenly stop emitting particles, the heliosphere would collapse inward as the interstellar medium rushed in to fill the void. The bubble would deflate like a punctured balloon, and within a few years, the interstellar medium would flood the space currently occupied by the solar wind, reaching all the way to the inner solar system. The planets would be bathed in interstellar plasma and exposed to the full intensity of galactic cosmic radiation. Earth's magnetic field would still provide some protection, but the overall radiation environment would change significantly. This is not going to happen anytime soon. The sun has been blowing its bubble for 4.5 billion years and will continue for roughly another 5 billion. But the heliosphere has not been constant over that time. As the sun moves through the galaxy, it encounters regions of the interstellar medium with different densities and pressures. When the surrounding medium is denser, the heliosphere shrinks. When it is thinner, the heliosphere expands. Over millions of years, the heliosphere has likely changed size dramatically, sometimes extending much farther than it does today, sometimes being compressed inward. There is evidence that the solar system may currently be passing through or near the edge of a region called the local interstellar cloud, a pocket of slightly warmer and denser material within the broader local bubble, a vast cavity of hot, sparse gas carved out by ancient supernovae. As the sun exits this cloud, possibly within the next few thousand years, the interstellar conditions pressing against the heliosphere will change, and the boundary will shift accordingly. The heliosphere is alive. It breathes with the solar cycle. It flexes with the interstellar weather. It leaks at its boundaries. It surprised scientists with features they never predicted. And it creates the most physically dramatic boundary in the solar system, not at the edge of the last planet, not at the farthest reach of gravity, but at the point where the sun's breath finally runs out of strength and the galaxy pushes back. What the Voyagers measured as they crossed that point is a story written in charged particles, plasma waves, and magnetic fields. And interpreting that story required instruments built in the 1970s, still functioning decades beyond their design life, sending data home at the speed of light from a place no human technology was ever expected to reach. On August 25th, 2012, something changed in the data streaming back from Voyager 1. The numbers had been shifting for months. a slow crescendo of galactic cosmic rays creeping upward, a gradual decline in the heliospheric particles that had accompanied the spacecraft for 35 years. But on that day, the change became decisive. The count of solar energetic particles did not just decrease, it collapsed. Within days, the population of lower energy particles originating from inside the heliosphere dropped to less than 1% of its previous value. Simultaneously, galactic cosmic rays, high-energy particles born in the violent remnants of exploded stars and accelerated by processes scattered across the Milky Way, rose to levels that had never been recorded by any instrument this close to the Sun. Voyager 1 was no longer swimming in the Sun's exhaust. It was immersed in the galaxy. But the Voyager science team did not immediately declare that the spacecraft had entered interstellar space. They hesitated. And that hesitation reveals something important about how science actually works at the boundary of the known. The problem was the magnetic field. Models had predicted that when Voyager crossed the heliopause, it would detect a change in the direction of the surrounding magnetic field. Inside the heliosphere, the magnetic field is the Sun's, carried outward by the solar wind and twisted into a spiral by the Sun's rotation. Outside the heliosphere, the magnetic field belongs to the interstellar medium, shaped by galactic-scale currents and the motions of nearby stars. These two fields were expected to point in different directions. When Voyager crossed the boundary, the direction should rotate, providing an unambiguous signal that the spacecraft had left the Sun's magnetic domain and entered the galaxies. It did not happen. The magnetic field direction barely changed. The magnitude shifted, but the orientation remained stubbornly parallel to what Voyager had been measuring inside the heliosphere. This threw the science team into months of careful analysis and heated discussion. Had Voyager actually crossed the heliopause? Or had it entered some previously unknown region within the heliosphere, where solar particles were depleted but the Sun's magnetic field still held sway? Some team members argued that without a clear magnetic field rotation, the crossing could not be confirmed. Others pointed to the particle data, which showed every hallmark of an environmental transition. The solar wind was gone. Galactic cosmic rays were at full strength. Something fundamental had changed. Magnetic field direction or not. The debate was resolved by an instrument that was never designed for this measurement, using a method that no one had originally planned. Voyager 1's plasma wave instrument, built to study plasma interactions near Jupiter and Saturn in the 1970s, detected oscillations in the surrounding electron gas. These oscillations are essentially vibrations in the plasma, analogous to sound waves in air. The frequency of these vibrations is directly related to the density of electrons in the surrounding medium. Higher density means higher frequency. By measuring the frequency, scientists could calculate the electron density of the plasma surrounding the spacecraft. In April of 2013, a solar eruption that had occurred more than a year earlier sent a pressure wave rippling outward through the heliosphere and into the nearby interstellar medium. When this wave reached Voyager 1's location, it set the surrounding plasma vibrating. The plasma wave instrument recorded oscillations at a frequency that corresponded to an electron density of approximately 0.08 electrons per cubic centimeter. This was roughly 40 times higher than the density of the solar wind plasma near the heliopause. It was consistent with the expected density of the local interstellar medium, derived from independent astronomical observations of the region surrounding the Sun. The spacecraft was unambiguously immersed in interstellar plasma, working backward from this measurement and analysing earlier, fainter plasma oscillation events. The science team determined that the density transition had occurred around August 25, 2012. That date became the official moment Voyager 1 entered interstellar space. The announcement came in September 2013, more than a year after the actual crossing, because science demanded certainty before celebration. The confirmation method itself was remarkable. The plasma wave instrument measures oscillations by detecting voltage fluctuations on two long antennas extending from the spacecraft body. These antennas pick up electric field variations in the surrounding plasma with extraordinary sensitivity. The instrument was designed for a 3-year planetary mission. By 2012, it had been operating for 35 years in the harshest radiation environment in the solar system's outer reaches, and it still functioned well enough to detect the faint hum of interstellar electrons vibrating in response to a solar storm. Without this instrument, the confirmation of Voyager 1's heliopause crossing would have been far more ambiguous and far more contentious. But Voyager 1 had a significant handicap. Its plasma science instrument, the tool specifically built to measure solar wind speed, density, and temperature by directly capturing incoming plasma particles, had failed in 1980. For 32 years before the heliopause crossing, Voyager 1 had been flying partially blind to the plasma environment around it. It could detect energetic particles, it could measure magnetic fields, it could listen for plasma wave oscillations, but it could not directly sample the bulk plasma, the slow-moving thermal particles that make up the majority of the solar wind and the interstellar medium. This meant that Voyager 1's crossing of the heliopause, while confirmed, was reconstructed from indirect evidence. The full, detailed picture of what happens to plasma at the boundary had to wait for Voyager 2. Voyager 2 reached the heliopause on November 5, 2018, 6 years and 2 months after its twin. It crossed at a different location, roughly along the southern flank of the heliosphere rather than near the nose where Voyager 1 had exited. It crossed at a different phase of the solar cycle, during a quieter period of solar activity, and crucially, its plasma science instrument was still working. For the first time in history, a functioning plasma detector directly measured the transition from solar wind to interstellar medium. What Voyager 2 found confirmed that the heliopause is not a simple surface but a structured transition with multiple layers, each representing a different stage of the solar wind's final compression against the interstellar medium. Approaching the boundary, the plasma instrument recorded a sequence of changes that revealed increasing compression, heating, and deceleration of the solar wind. The transition involved a broad outer boundary region where conditions shifted gradually, followed by a much thinner inner layer where changes became abrupt, and finally the heliopause crossing itself, which was remarkably sharp. The full details of this crossing sequence emerged through the instrument measurements that revealed each layer as Voyager 2 passed through it. But the structural lesson was immediately clear. The heliopause is not a membrane. It is a nested series of compression fronts, each one thinner and more intense than the last, culminating in a final transition so rapid that it occurred within hours. The solar wind does not fade out at the heliopause. It is crushed into progressively denser layers until it can be compressed no further, and then the interstellar medium begins. Voyager 2's crossing also revealed that the interstellar side of the heliopause held its own surprises. The temperature of the interstellar plasma just beyond the boundary was significantly higher than theoretical predictions for the undisturbed interstellar medium. The region immediately outside the heliopause is heated and compressed by the heliosphere's presence, creating a disturbed zone that scientists now call the very local interstellar medium. This zone extends outward from the heliopause for an unknown distance, and neither Voyager has yet travelled far enough to reach undisturbed interstellar conditions beyond it. And the environment on the far side of that final transition held its own surprises, ones that revealed the heliopause is not where the sun's influence truly ends, but the interstellar side held surprises of its own. The plasma just beyond the heliopause was hotter than models had predicted. Temperatures in the very local interstellar medium measured by Voyager 2 were significantly higher than predicted, confirming what Voyager 1's indirect measurements had suggested. This excess heat confirmed what Voyager 1's indirect measurements had suggested. The region immediately outside the heliopause is not the calm, pristine galactic environment that exists far from any star. It is a disturbed zone, heated and compressed by the heliosphere's presence. The sun's bubble does not simply end at the heliopause. It modifies the interstellar medium around it, warming and compressing the nearby gas, creating a jacket of perturbed material that surrounds the bubble like an atmosphere surrounds a planet. Voyager 2 also confirmed the magnetic field mystery that had complicated Voyager 1's crossing. The interstellar magnetic field measured by Voyager 2 was, once again, roughly parallel to the heliospheric magnetic field measured just inside the boundary. Two crossings at different locations, different times, and different solar cycle phases both showed the same alignment. Whatever process aligns, these fields appears to operate consistently around the heliosphere. Some researchers have proposed that the interstellar magnetic field, as it drapes around the heliosphere, gets bent and compressed in a way that happens to align with the internal solar magnetic field along the boundary. Others suggest that magnetic reconnection, a process where opposing magnetic field lines break and reconnect in a different configuration, actively rearranges the field geometry at the heliopause. The answer remains uncertain, but the observation is robust. One of the most intriguing details from Voyager 2's crossing involves the porosity of the heliopause. While Voyager 1 exited near the nose of the heliosphere, where the boundary is most directly facing the incoming interstellar medium, Voyager 2 exited along the flank. At this flanking location, the heliopause appeared to be more permeable. One of Voyager 2's particle instruments detected a trickle of heliospheric particles leaking outward through the boundary into interstellar space. The heliopause was not perfectly sealed. Solar material was escaping. The hull of the Sun's ship was somewhat leaky, and the leak rate appeared to depend on location. Regions closer to the nose were tighter. Regions along the flanks allowed more seepage. This observation has implications for how efficiently the heliosphere contains solar material, and for how much solar origin plasma contaminates the nearby interstellar medium. Both Voyager spacecraft also measured changes in cosmic ray populations that provided independent confirmation of the heliopause crossing. Inside the heliosphere, the Sun's magnetic field acts as a partial shield against galactic cosmic rays. These highly energetic particles, predominantly protons accelerated to near-light speeds by astrophysical processes elsewhere in the galaxy, are deflected and decelerated as they attempt to penetrate the magnetized solar wind. This process is called solar modulation. Deep inside the heliosphere, near Earth, galactic cosmic ray intensities are significantly reduced compared to what exists in the open interstellar medium. The reduction varies with the solar cycle, stronger during solar maximum when the heliospheric magnetic field is more complex and turbulent, weaker during solar minimum when the field is more ordered and easier for particles to navigate. As the Voyagers move through the heliosheath toward the heliopause, galactic cosmic ray intensities steadily increased, reflecting the weakening of solar modulation at greater distances from the Sun. When each spacecraft crossed the heliopause, cosmic ray levels jumped to their highest recorded values and then stabilized, no longer increasing with distance. This plateau represented the unmodulated galactic cosmic ray intensity, the full strength of the cosmic ray flux as it exists in the interstellar medium, unfiltered by the Sun's magnetic influence. For the first time, scientists had a direct measurement of the cosmic ray environment that bathes the galaxy between the stars. This measurement is invaluable for understanding radiation risks for any future spacecraft or crew that might one day travel beyond the heliosphere. Complementing the Voyager measurements, a separate spacecraft much closer to home was observing the heliosphere's boundary from the inside, using an entirely different technique. The Interstellar Boundary Explorer, IBEX, launched in October 2008, orbits Earth and collects energetic neutral atoms that originate at the heliosphere's edge. These atoms begin their lives as charged particles, ions in the heliosheath, or the very local interstellar medium that are moving at high speeds. When one of these ions collides with a slow-moving neutral hydrogen atom, it can steal an electron, becoming electrically neutral. Once neutral, it is no longer trapped by magnetic fields. It flies in a straight line, carrying information about the plasma conditions at its point of creation across the billions of miles separating the heliosphere's edge from Earth. IBEX intercepts these atomic messengers and measures their energy and arrival direction, constructing maps of the heliosphere's boundary that would otherwise be entirely invisible. IBEX's most startling discovery was the ribbon, a narrow band of enhanced energetic neutral atom emissions stretching across a broad arc of the sky. The ribbon appeared in IBEX's first all-sky maps, published in 2009. and it stunned the heliophysics community. No existing model had predicted anything like it. The ribbon roughly traces the region where the external interstellar magnetic field is perpendicular to the line of sight from the Sun, suggesting a deep connection between the ribbon and the geometry of the galactic magnetic field pressing against the heliosphere. Several competing explanations have been proposed. One leading hypothesis involves a secondary charge exchange process. Solar wind ions that escape the heliosphere and become pickup ions in the interstellar medium are captured by the interstellar magnetic field. Where that field happens to point radially back toward the Sun, the resulting energetic neutral atoms travel directly inward and are detected as a concentrated ribbon. Another hypothesis suggests the ribbon marks a region of enhanced magnetic pressure on the heliosphere's boundary. The debate is ongoing, and resolving it is one of the primary objectives of the IMAP mission. IBEX also mapped a broader feature called the globally distributed flux, a more diffuse population of energetic neutral atoms originating from the heliosheath across the entire sky. This background signal provides information about the overall structure of the heliosheath and how plasma is distributed throughout it. By combining the ribbon signal with the globally distributed flux, scientists have begun constructing three-dimensional models of the heliosphere's shape that go beyond what the Voyager point measurements alone could provide. IBEX sees the big picture. Voyager sees the local detail. Together, they provide complementary views of the same boundary. IMAP, which launched on September 24, 2025, and reached its operational orbit at the first Sun-Earth Lagrange point in January 2026, represents the next generation of this remote sensing approach. Its three energetic neutral atom detectors, IMAP Low, IMAP High, and IMAP Ultra, offer approximately 15, 25, and 35 times greater collection power than their IBEX predecessors, respectively. This means IMAP can produce maps of the heliosphere's boundary with roughly 4-degree angular resolution and revisit times of approximately 1 week to 3 months, depending on the instrument. For context, IBEX required 6 months to produce a single all-sky map at a much coarser resolution. IMAP will track how the heliosphere's boundary evolves with the solar cycle in near real time, watching the heliopause shift, the ribbon fluctuate, and the heliosheath respond to solar eruptions, all from a vantage point 1 million miles from Earth. IMAP also carries instruments that directly measure the solar wind, energetic particles, and interstellar dust at its location near Earth. This allows scientists to correlate conditions at the source, the outgoing solar wind, with conditions at the boundary, the heliosheath and heliopause, creating a connected picture of cause and effect across the entire heliosphere. When a coronal mass ejection erupts from the Sun, IMAP will measure it as it leaves. Months or years later, the energetic neutral atom detectors will observe the boundary's response when that eruption's pressure wave eventually reaches the heliopause. This kind of connected, time-resolved observation has never been possible before. Additionally, IMAP's interstellar dust experiment, IDEX, will make direct measurements of interstellar dust grains, tiny particles composed of rocky or carbon-rich material that originated outside the solar system, likely from the aftermath of ancient supernova explosions. These grains flow into the heliosphere from the interstellar medium, and their composition provides a chemical fingerprint of the galactic material surrounding our solar neighborhood. By analyzing these dust grains, scientists will learn about the makeup of the interstellar medium without sending a spacecraft to its outer reaches. Every dust particle intercepted by IMAP is a sample of the galaxy delivered to our doorstep. There is another spacecraft whose role in this story is still unfolding. NASA's New Horizons probe, famous for its historic flyby of Pluto in 2015 and its subsequent encounter with the Kuiper Belt object Arrokoth in 2019, is currently travelling through the outer heliosphere at a distance of roughly 60 astronomical units from the Sun. It is not yet near the termination shock, but it is already returning data that no other active spacecraft can provide from that region of space. New Horizons occupies a unique position in heliospheric science. Voyager 1 and Voyager 2 crossed the outer heliosphere decades ago, but their instruments were designed in the 1970s, and several key sensors had already degraded or failed by the time the spacecraft reached the most scientifically interesting regions. New Horizons carries more modern instrumentation, including the solar wind around Pluto instrument, SWAP, which measures the solar wind's speed, density, and temperature, and the Pluto Energetic Particle Spectrometer Science instrument, PEPSI, which detects energetic ions and electrons. These instruments are actively measuring conditions in the distant solar wind that the Voyagers could no longer fully characterize by the time they were at comparable distances. One of New Horizons' most significant contributions to heliospheric science has been the first direct detection and measurement of interstellar pickup ions in the outer heliosphere. The physics of how these ions form and accumulate was understood theoretically, but no spacecraft had ever directly measured their abundance and energy distribution at the distances where they were predicted to dominate the solar wind's pressure budget. New Horizons changed that. Its SWAP instrument captured pickup ions in sufficient detail to confirm that they are not just present in the outer solar wind but are reshaping it. The measurements showed that the solar wind at 60 astronomical units is a fundamentally different fluid than the solar wind near Earth, loaded with energetic particles born from interstellar material that the heliosphere could not keep out. This matters for understanding the termination shock. The properties of the termination shock, its strength, its structure, and the degree to which it decelerates and heats the solar wind depend critically on the composition of the incoming plasma. A solar wind loaded with energetic pickup ions behaves differently at a shock front than a pure solar wind without them. Pickup ions carry a disproportionate share of the energy and pressure, which can weaken the shock and spread its effects over a broader region. New Horizons' measurements of the pickup ion population upstream of the termination shock will allow scientists to predict the shock's properties far more accurately than was possible with Voyager data alone. If New Horizons survives long enough, and current power projections suggest it may remain operational into the late 2030s or early 2040s, it could become the third spacecraft to cross the termination shock and enter the heliosheath. Its trajectory is carrying it in a direction roughly between the paths taken by the two Voyagers, providing a third sampling point along the heliosphere's boundary surface. 3-point measurements would vastly improve constraints on the termination shock's shape and variability compared to the 2 points provided by Voyager alone. Power remains the limiting factor. Like the Voyagers, New Horizons is powered by a radioisotope thermoelectric generator whose output declines steadily with time. Engineers are carefully managing power consumption to extend the spacecraft's scientific life as long as possible, prioritizing the heliospheric instruments that will return the most valuable data as the spacecraft moves deeper into unexplored territory. New Horizons will almost certainly not reach the heliopause, which lies decades of travel beyond the termination shock. But if its power supply holds as projected, it may cross the termination shock and return measurements from the heliosheath that would complement the Voyager data from a third direction along the boundary. In the meantime, the data it is collecting right now, in the vast, poorly understood region between the Kuiper Belt and the termination shock, fills a gap that the Voyagers left behind. The Voyagers raced through this region with aging instruments decades ago. New Horizons is measuring it with modern detectors in the present, providing a baseline that will help scientists connect the solar wind conditions at the source with the boundary conditions the Voyagers measured at the edge. It is stitching together the middle of the story, the billions of miles of gradual transformation where the solar wind evolves from a fast, hot, relatively simple outflow into the complex, pickup ion-laden, slowing plasma that eventually crashes into the termination shock and begins its final journey toward the heliopause. The combination of Voyager's in-place measurements, IBEX's decade-plus of remote mapping, and IMAP's vastly improved capabilities is creating an increasingly detailed and nuanced picture of the heliosphere's boundary. But that picture contains a crucial lesson that goes beyond any single measurement or any individual instrument's data. The boundary where interstellar space begins is not a static feature drawn on a map. It is a living, dynamic, breathing interface between the Sun and the galaxy. It shifts with the solar cycle. It responds to individual solar eruptions. It varies from one location to another around the heliosphere's surface. It is more permeable in some regions and tighter in others. It heats the surrounding interstellar medium and is in turn shaped by that medium's pressure and magnetic field. It produces structures, like the ibex ribbon, that emerge from the interaction between solar and galactic physics in ways that scientists are still working to understand. The measurements also carry a humbling reminder about the nature of exploration at these distances. Voyager 1 and Voyager 2 are the only human-made objects to have directly sampled the heliopause and the very local interstellar medium. They represent 2 points of measurement along a boundary that stretches across a surface area of hundreds of billions of square astronomical units. Drawing conclusions about the entire heliosphere from 2-point measurements is like dipping a finger into the ocean at 2 beaches and trying to infer the temperature, salinity, and current patterns of every ocean on Earth. The Voyager data is precious, irreplaceable, and profoundly limited. IBEX and IMAP help enormously by providing global maps, but those maps are constructed from particles that have travelled billions of miles and carry only indirect information about the conditions at their origin. Every measurement involves inference. Every conclusion carries uncertainty. This is why the scientific community was so careful in declaring when and where Voyager 1 crossed the heliopause. This is why the announcement came a full year after the event. This is why the debate about the magnetic field alignment continues years later. And this is why new missions like IMAP are essential. The boundary is confirmed. It is real. It is measurable. But it is not fully understood. Every new dataset reveals complexity that was previously hidden. Every answer generates new questions. The instruments have told us that the boundary exists and roughly where it is. They have told us what changes when you cross it. They have told us that the transition is sharper than some expected and more layered than others predicted. They have told us that the region beyond is not the undisturbed galactic void of simple models, but a dynamic zone still echoing with the Sun's influence. What the instruments have not yet told us is what lies farther out. Voyager 1, the most distant human-made object, is still measuring conditions in the perturbed, very local interstellar medium, a zone whose outer boundary has not yet been reached. Somewhere beyond Voyager's current position, the disturbances caused by the heliosphere's presence in the interstellar medium will fade. The plasma density will stabilize at the true background level of the local interstellar cloud. The temperature will drop to the undisturbed value. The magnetic field will settle into its ambient galactic configuration, no longer distorted by the nearby heliosphere. That transition, from the perturbed very local interstellar medium to the undisturbed interstellar medium, represents yet another boundary, one that no instrument has yet crossed. Beyond that boundary lies true interstellar space, the medium that fills the vast distances between stars, composed of gas and dust and cosmic rays and magnetic fields that know nothing of the Sun and owe nothing to its influence. That medium stretches for light years in every direction, interrupted only by the occasional astrosphere of another star, each one blowing its own bubble, each one creating its own boundary, where stellar influence ends and galactic space begins. Voyager will never reach undisturbed interstellar space in any meaningful sense. Its power supply is fading. The radioisotope thermoelectric generators that convert the decay heat of plutonium-238 into electricity produce less power with every passing year. In the late 2020s, the remaining science instruments will be shut down one by one as power dwindles. By the early 2030s, Voyager 1 will likely fall silent, its transmitter too weak to reach Earth, its instruments too starved of power to function. It will continue travelling outward at the same steady speed it has maintained for decades, a cold and silent artifact, still pointed toward a home that stopped listening long ago. But the data it has already sent home, the data Voyager 2 continues to return, and the maps that IBEX has built and IMAP is now refining, have permanently changed our understanding of where the Sun's influence ends. The boundary is not a clean line. It is not a wall. It is a region layered and dynamic, sharp in some measurements and gradual in others. It is defined by the fading pressure of the solar wind, the compression of plasma, the transition of magnetic fields, and the flood of galactic cosmic rays replacing solar particles. It is confirmed by direct measurement, corroborated by remote sensing, and still yielding surprises with every new observation. The instruments found the boundary. What remains is understanding what it means to cross it, not just for a spacecraft carrying outdated electronics and a golden phonograph record, but for the future of a species that has only just begun to comprehend the scale of the space it inhabits. Voyager 1 is in interstellar space. This statement is true, and it is misleading at the same time. It is true because the spacecraft has crossed the heliopause and is now immersed in interstellar plasma, dominated by galactic rather than solar material. It is misleading because Voyager 1 has not left the solar system. Not even close. Understanding this distinction is essential to grasping what the boundary really means, why it matters, and why the phrase "the edge of the solar system" is one of the most persistently misunderstood concepts in modern astronomy. The heliopause sits at roughly 120 astronomical units from the Sun. The outer edge of the Oort cloud may extend to 100,000 astronomical units. These two numbers differ by a factor of approximately 800. Think of the Sun as a campfire on an open plain at night. The heliosphere is the circle of warmth and light surrounding the fire. Step beyond that circle and you feel the cold immediately. The wind hits your face, the darkness closes in. That is the heliopause. But the plain itself, the land you are standing on, stretches for miles in every direction, and it all belongs to the same terrain. The Oort cloud is that vast plain, still the Sun's gravitational territory, even though the warmth of the fire stopped reaching you long ago. Voyager has stepped beyond the firelight. It will be walking across the plain for tens of thousands of years before it reaches land that belongs to another fire. This is not a technicality. It reflects a fundamental difference in the physical processes that define each boundary. The heliopause marks the edge of the Sun's particle and magnetic influence, the point where the solar wind's outward pressure finally yields to the interstellar medium's inward pressure. It is a plasma boundary. The Oort cloud boundary marks the edge of the Sun's gravitational dominance, the point where the tidal forces of the Milky Way and the gravitational pulls of nearby passing stars begin to overcome the Sun's hold on orbiting objects. It is a gravitational boundary. These are two entirely different physical regimes operating on vastly different scales. A spacecraft can be in interstellar space by the plasma definition, while remaining deeply embedded in the solar system by the gravitational definition. That is exactly where Voyager sits today. The region between the heliopause and the Oort cloud is one of the least explored and least understood volumes of space in our entire solar system. It is technically interstellar, meaning the ambient plasma and magnetic field belong to the galaxy rather than the Sun. But it is also technically solar, meaning objects within it still orbit the Sun and are gravitationally bound to our star. This enormous volume, stretching from roughly 120 astronomical units to perhaps 100,000, contains the Oort cloud's trillions of icy bodies, drifting on orbits so vast and so slow that a single revolution can take millions of years. It contains interstellar gas and dust flowing through the Sun's gravitational sphere as though the boundary did not exist, because gravity does not stop neutral particles from passing through, and it contains the fading influence of the Sun itself, its light growing dimmer, its gravitational pull growing weaker, but never quite reaching zero until you cross that final gravitational threshold where the galaxy claims dominance. Voyager 1 will not reach even the inner fringe of the Oort cloud for centuries after its instruments have fallen silent. Emerging from the far side, where the Sun's gravitational hold finally yields to the galaxy, will take an almost incomprehensible span of time longer, a journey measured not in centuries but in tens of millennia. During that immense journey, Voyager will be silent. Its power supply will have failed millennia earlier. Its instruments will be dead. Its radio transmitter will be mute. The spacecraft will coast as a cold, inert artifact, carrying its golden record through a region of space that no human technology has ever measured and none is currently planned to reach. The Oort cloud will remain, for the foreseeable future, the largest unexplored territory in our solar system. We know it must exist based on the orbits of long-period comets. We have never detected a single object confirmed to reside within it. The interstellar medium that Voyager now travels through deserves attention in its own right, because most people imagine the space between stars as empty. It is not. The interstellar medium is a vast, tenuous, but physically real substance that fills the galaxy. It is composed primarily of hydrogen and helium, with trace amounts of heavier elements. Some of this material exists as neutral atoms, some is ionized into plasma, some is locked into tiny dust grains, microscopic particles of silicate, carbon, and ice that drift through the galaxy on timescales measured in millions of years. The interstellar medium is thin beyond earthly comprehension, typically containing only about 0.1 to 1 atom per cubic centimetre in the Sun's local neighbourhood. For comparison, a typical high-quality laboratory vacuum on Earth still contains roughly 100,000 molecules per cubic centimetre, and even the most extreme vacuum chambers ever built hold at least 100 particles per cubic centimetre. The interstellar medium is emptier than anything humanity has ever manufactured on Earth. Yet across the immense volumes of interstellar space, this vanishingly thin material adds up. The total mass of the interstellar medium in the Milky Way is estimated at 10 to 15% of the galaxy's total visible mass. It is the raw material from which new stars and planetary systems form. It is the repository of elements forged in the cores of dead stars and scattered by supernovae. The carbon in your bones, the oxygen in your lungs, the iron in your blood were all once part of the interstellar medium, adrift between the stars before gravity collected them into the cloud that collapsed to form our Sun and its planets 4.5 billion years ago. The particular patch of interstellar medium surrounding our solar system has its own characteristics and its own history. The Sun currently resides within or near the edge of a small, warm cloud of interstellar gas called the local interstellar cloud, sometimes known as the local fluff. This cloud is roughly 30 light-years across and warm by interstellar standards, though still far cooler than the perturbed plasma the Voyagers measured immediately outside the heliopause. The local interstellar cloud is itself embedded within a much larger structure called the local bubble, an irregularly shaped cavity of hot, sparse gas stretching roughly 1,000 light-years across that was carved out by approximately 15 supernova explosions that occurred in the Sun's neighbourhood over the past 14 million years. These explosions swept the region clean of denser interstellar material, leaving behind a bubble of extremely hot, extremely thin gas. The local interstellar cloud appears to be a fragment of denser material that survived within or drifted into this larger cavity. The Sun's motion through the local interstellar cloud, the same motion that gives the heliosphere its asymmetric shape, means the Sun may exit this particular cloud within the next few thousand years, entering a region of different density and temperature. When this happens, the interstellar medium pressing against the heliosphere will change. If the new environment is denser, the heliosphere will be compressed, shrinking the distance to the heliopause. If it is less dense, the heliosphere will expand. The radiation environment inside the heliosphere, including at Earth, could change measurably. Galactic cosmic ray intensities at Earth's surface are modulated by the heliosphere's size and strength. A smaller heliosphere means less shielding and more cosmic ray exposure. Some researchers have speculated that past variations in the heliosphere's size, driven by the Sun's passage through different interstellar environments, may have influenced Earth's climate and biological evolution over geological timescales. The evidence for this is circumstantial and debated, but the physical mechanism is real. The heliosphere is not just an abstract boundary far from home. It is a shield, and its strength depends on what lies beyond it. This brings us to why the boundary matters for the future of human exploration. Any spacecraft, crude or robotic, that ventures beyond the heliopause will face a radiation environment fundamentally different from anything encountered within the solar system. The heliosphere's shielding effect against galactic cosmic rays, which the Voyagers quantified by measuring the dramatic increase in cosmic ray intensity as they crossed the heliopause, has direct consequences for any future mission beyond the bubble. At Earth's orbit, that shielding reduces cosmic ray exposure by a factor of several compared to the unshielded interstellar environment. Beyond the heliopause, the full intensity of galactic cosmic radiation arrives from all directions with nothing to deflect it. These are not ordinary particles. Galactic cosmic rays include protons, helium nuclei, and heavier ions accelerated to enormous energies by supernova remnants, pulsar wind nebulae, and other violent astrophysical phenomena. Some galactic cosmic rays carry energies billions of times higher than the particles produced in the most powerful accelerators on Earth. When these particles strike biological tissue, they deposit energy along their paths, breaking molecular bonds, damaging DNA, and producing cascades of secondary particles that spread the damage over a wider area. The health effects of prolonged exposure to galactic cosmic radiation are a subject of active research and significant concern for any crewed missions beyond the inner solar system. Astronauts on the International Space Station, protected by Earth's magnetic field and partially shielded by the heliosphere, receive radiation doses roughly 10 to 20 times higher than the average person on the ground. Beyond the heliopause, with no heliospheric shielding, those doses would increase further. Long-duration missions to interstellar space, however far in the future they may lie, will need to solve the radiation problem or accept substantial health risks for their crews. The heliopause boundary also matters for understanding the habitability of other planetary systems. Every star with a stellar wind creates its own analogue of the heliosphere, called an astrosphere. The size and strength of each astrosphere depend on the star's wind intensity and the density of the surrounding interstellar medium. Hot, luminous stars with powerful winds create enormous astrospheres that shelter vast volumes of space from galactic cosmic radiation. Cooler, smaller stars with weaker winds create smaller, more fragile astrospheres that provide less shielding. Some stars may have astrospheres so small that their planets are bathed in nearly unshielded galactic cosmic radiation for their entire existence. This has implications for the search for habitable worlds. A planet in the habitable zone of its star, where temperatures allow liquid water, might still be inhospitable if its star's astrosphere provides insufficient cosmic ray shielding. High levels of cosmic radiation can strip planetary atmospheres, break down complex molecules on surfaces, and increase mutation rates in biological organisms beyond levels compatible with the evolution of complex life. The habitability of a planet depends not only on its distance from its star and the composition of its atmosphere, but on the star's ability to create a protective bubble against the galactic radiation environment. Studying our own heliosphere, mapping its boundaries, and understanding the physics that determine its size and effectiveness provides a template for evaluating whether distant exoplanetary systems offer similar protection. NASA's IMAP mission, now operational, is contributing directly to this broader understanding. By mapping the heliosphere's boundary with unprecedented resolution and tracking how it responds to changes in solar activity and interstellar conditions, IMAP will help refine models of astrospheric physics that can be applied to other stars. Understanding how the sun's bubble interacts with the local interstellar cloud informs predictions about how a sun-like star's astrosphere would behave in a denser or thinner interstellar environment. If the heliosphere were significantly smaller, perhaps due to a weaker solar wind or a denser surrounding medium, the radiation environment at Earth's orbit would change. How much change can a biosphere tolerate? At what point does reduced astrospheric shielding make a planetary surface uninhabitable? These questions connect the physics of the heliopause directly to the search for life in the galaxy. There is a deeper reason why the discovery and characterization of this boundary matters, one that extends beyond radiation shielding and mission planning. The heliopause represents the limit of the sun's active influence on its environment. Inside the heliosphere, The Sun is not just a light source, it is an environmental engineer. Its wind shapes the plasma environment. Its magnetic field organizes charged particles into structured patterns. Its eruptions send shock waves rippling across billions of miles. Its radiation pressure pushes dust grains and alters the trajectories of comets. The Sun's influence is not passive. It is dynamic, continuous, and extends across a volume of space large enough to swallow the orbits of every planet many times over. At the heliopause, that influence ends. Beyond the boundary, the Sun is just a star. A bright point of light, the brightest in the local sky, but no longer the dominant force in the surrounding environment. The plasma belongs to the galaxy. The magnetic field belongs to the galaxy. The energetic particles belong to the galaxy. The Sun's gravity still reaches far beyond the heliopause, holding the Oort cloud in its grip. But gravity is silent and passive compared to the active, dynamic influence of the solar wind and magnetic field. Crossing the heliopause means crossing from a region where the Sun controls the local physics to a region where the Sun is merely a gravitational anchor surrounded by someone else's weather. This transition is what Voyager measured. Not a wall, not a door. A change in ownership. A shift in which forces dominate, which particles fill the space, and which magnetic field organizes the plasma. The transition is physically sharp in some measurements, occurring over hours or days, and gradual in others, unfolding over astronomical units of distance. It is different in different locations around the heliosphere. It varies with time as the Sun's activity waxes and wanes. It is leaky in some places and sealed in others. It is heated where it should be cool and magnetically aligned where it should be disordered. It defies the simplest models while confirming the fundamental prediction that such a boundary must exist wherever a stellar wind meets the interstellar medium. Every star in the galaxy faces the same physics. Every star with a wind blows a bubble. Every bubble has a boundary. Every boundary marks the transition from stellar space to interstellar space. The heliosphere is not unique. It is one example of a universal process, repeated hundreds of billions of times across the Milky Way, wherever stars burn and winds blow. What makes our heliosphere special is not its physics. It is that we are inside it, that we have instruments capable of measuring it, and that we have, for the first time in the history of any species we know of, sent objects across it and listened to what they found. The Voyager spacecraft will continue coasting outward long after its instruments fall silent. Voyager 1, the more distant of the pair, will pass within approximately 1.6 light-years of the star AC plus 793888, also known as Gliese 445, in the constellation Camelopardalis, in roughly 40,000 years. Gliese 445 is a red dwarf considerably dimmer than our Sun, and Voyager will not come close enough to interact with any planetary system it might possess. Voyager 2 will pass within about 1.7 light-years of the star Ross 248 in roughly 40,000 years. Neither spacecraft will encounter anything. They will drift through the interstellar medium as inert metal shells, gradually eroded by cosmic dust impacts over millions of years, carrying their golden records into a silence so vast and so permanent that no one will ever play them. But the data they have already transmitted has changed something irreversible in how humanity understands its position. Before Voyager, the heliopause was a theoretical prediction, a line on a diagram, a boundary that models said should exist but that no instrument had directly confirmed. After Voyager, it is a measured reality. Scientists know its approximate distance. They know the plasma density on either side. They know the magnetic field behavior at the crossing. They know the cosmic ray intensity in the unshielded interstellar medium. They know the temperature of the local interstellar plasma. They know that the boundary is sharper than some expected and more dynamic than others predicted. They know that the region just beyond it is perturbed and complex, not the calm void of simple models. They know that the Sun's influence does not end cleanly but fades through a series of layers, each one defined by a different physical process, each one located at a different distance, each one telling a different story about the Sun's relationship with the galaxy that hosts it. This knowledge carries a weight that goes beyond the technical details of plasma densities and magnetic field orientations. It tells us something about the nature of boundaries in the cosmos. The universe does not draw sharp lines. It creates gradients. The transition from day to night is not a boundary, but a curve. The edge of Earth's atmosphere is not a surface, but a gradual thinning that fades across hundreds of miles. The border between land and ocean shifts with every wave. In the same way, the boundary between solar space and interstellar space is not a wall, but a transition. Layered and dynamic, sharp in some variables and gradual in others, real enough to measure but too complex to capture in a single number or a single definition. The solar system does not end. It fades. It fades at the orbit of Neptune, where the ordered architecture of major planets gives way to the scattered debris of the Kuiper belt. It fades at the heliopause, where the Sun's plasma influence yields to the galactic medium. It fades at the outer Oort cloud, where the Sun's gravity loosens its final grip and the galaxy claims what lies beyond. Each boundary is real. None of them is the edge. Together, they define a nested series of transitions that trace the declining reach of one ordinary star in one ordinary arm of one ordinary galaxy. And this is what makes the discovery quietly unsettling, not in the dramatic way of science fiction, not with alien threats or cosmic disasters, but in the way that any honest confrontation with scale tends to unsettle. The Sun is powerful. It sustains all life on Earth. It drives the weather, the water cycle, and the entire biosphere. Its gravitational grip holds 8 planets, hundreds of moons, millions of asteroids and comets, and trillions of icy bodies in orbits that span light years. It has been burning for 4.5 billion years and will continue for 5 billion more. By any human standard, the Sun is overwhelming in its power and permanence. And yet, its plasma influence extends only 120 astronomical units before the galaxy pushes it back. That distance is enormous by earthly standards, more than 11 billion miles, but it is microscopic by galactic standards. The nearest star, Proxima Centauri, is approximately 268,000 astronomical units away. The heliopause occupies less than 1/20th of 1% of the distance to the nearest neighbouring star. The Sun's active domain, the region where it controls the local environment rather than merely illuminating it, is a tiny pocket of influence in a galaxy that stretches 100,000 light-years from edge to edge. The heliosphere is a shelter. It is real, and it is measurable, and it works. It deflects cosmic rays. It moderates the radiation environment. It protects the planets from the unfiltered harshness of galactic space. But it is also fragile. It depends on the continuous output of the solar wind, which depends on the corona's extreme temperature, which depends on magnetic processes that scientists still do not fully understand. If the Sun were to undergo a prolonged period of significantly reduced activity, the heliosphere would shrink. If the solar system were to pass through a dense cloud of interstellar material, the heliosphere would be compressed. The shelter is maintained by an ongoing expenditure of energy and matter, a constant act of inflation against the relentless inward pressure of the interstellar medium. Beyond the heliosphere, the interstellar medium waits. It was here before the Sun formed. It will be here after the Sun dies. When the Sun exhausts its hydrogen fuel and swells into a red giant in roughly 5 billion years, its intensified radiation and expanded atmosphere will briefly push the heliosphere outward. Then, as the Sun sheds its outer layers and contracts into a white dwarf, the solar wind will weaken and eventually cease. The heliosphere will collapse. The interstellar medium will flood inward, filling the space where the solar wind once blew. The planets, if any survive the red giant phase, will be bathed in interstellar plasma. The Oort cloud's icy bodies will continue orbiting the fading white dwarf for trillions of years, but the bubble will be gone. The boundary will no longer exist, because the process that created it will have stopped. This is what 2 small spacecraft found at the edge of the Sun's breath. Not a wall, not a gate, not a line drawn in the void. A transition defined by the fading reach of one star, real enough to measure, complex enough to surprise, and temporary enough to remind us that even the sun's power has limits. The boundary where interstellar space begins is not the edge of everything. It is the point where the sun stops shaping its surroundings and the galaxy takes over. It is the place where the shelter ends and the open sky of the Milky Way begins. And the most remarkable thing about it is not that it exists, it is what we found. 2 spacecraft built with 1970s technology, powered by the radioactive decay of a few kilograms of plutonium, carrying instruments less sophisticated than a modern smartphone, crossed a boundary that scientists had debated for decades, measured what they found, and transmitted the results back to Earth at the speed of light from 11 billion miles away. The signal took over 17 hours to arrive. It carried fewer watts of power than a refrigerator light bulb, and it told us, for the first time, exactly what happens when the sun lets go.